Hi everyone, Mrs. Casey here. Today's focus is on graphing rational functions. We're going to spend a couple of days on this topic, so make sure you're taking good notes on it because it is a little bit tricky. And then make sure you ask questions or you send us an email or put questions in the document to help get them answered as soon as possible. We are going to start with a couple of warm-up things. So the first warm-up that we're going to do is about limits. So here we have a graph and we want to determine the limits based on the graph. I'm going to highlight different things to help us see what the answers are to these problems. So the limit as x approaches negative infinity is found as we go off to the left. That limit is then approaching that horizontal asymptote of 4. Ooh, I thought that would look better than it did. Okay. Then as we go off to positive infinity, that's this part of the graph right here. And that also happens to be approaching that horizontal asymptote of 4. Now we have two different vertical asymptotes that we're looking at from the right and the left. As we approach 3 from the right, that's this portion of the graph, and that is going to positive infinity. As we approach 3 from the left, that is this portion of the graph, and that is also positive infinity. As we approach negative 3 from the left, that is this portion of the graph, and that is negative infinity. And as we approach negative 3 from the right, that is that portion of the graph I just highlighted, and that is heading towards positive infinity. I hope you remember how to do those. And again, if you don't, make sure you write it down so that you can ask questions. Now we're going to review the end behavior rules of rational functions. You've already done this, so hopefully as I talk about them, you'll remember the rules. When you're looking at these end behavior rules and you're taking the limits towards infinity, it's the same as literally remembering the numerator greater than, equal to, or less than the denominator. So in this first problem, the numerator's highest power is less than the denominator's highest power. It's to the first power over to the second power. And when this occurs, your limit is equal to 0, and it actually creates that horizontal asymptote at y equals 0. So the limit and the horizontal asymptote are all related, connected to the end behavior rules. Okay, this one here, the highest power in the numerator is 1, and the highest power in the denominator is also 1. So they're equal to each other. When this happens, the horizontal asymptote is the leading coefficients in front of those highest powered x's. So in this case, that's 5/3. And again, that's the horizontal asymptote now. So 5/3 is your horizontal asymptote. Okay, this last one, we now have the highest power in the numerator is greater than the highest power in the denominator. In this case, it's 1 degree higher. That's only important because we're going to do like a quick little division problem to see, again, what it's behaving like at the far reaches of the graph. So I'm taking that x squared over that x, and when I divide that out, I get something that's behaving like y equals x at the far reaches of the graph. And we know that y equals x is up on the right and down on the left. So this limit is infinity. There is actually no horizontal asymptote, and it creates what you will be learning about tomorrow, which is an oblique asymptote. Okay, so no horizontal creates an oblique asymptote that we will talk about tomorrow. Okay, so let's just start listing out some of the important things that you need to be able to do or find when you are graphing a rational function. I don't like that font or that color. Here we go. So here are some of the things that you need to be able to do. The very important thing is you really need to be able to factor the problem first. So if it can be factored, you want to make sure that you do that in your very first step, or nearly the first step, because it can cause you to create too many x-intercepts or too many vertical asymptotes, or not get the right horizontal asymptote if you don't factor first. Then you want to make sure that you can find any vertical asymptotes. There could be more than one. Oops. You want to find horizontal asymptotes. So there will only be one if there is one. Can only be one, sometimes none. Okay. You want to find any removable discontinuities. Remember, those are holes in the graph. And you want to find any x-intercepts. There can be more than one. And you want to find y-intercept. There can only be one of these, sometimes none. And I should probably add that there doesn't have to be a vertical. There can be more than one, but sometimes none. And the same thing here, there can be more than one, but sometimes none. Just depends on the problem. But the main thing to remember, though, about that stuff is there's ever only one y-intercept. Can't have two. And the same thing with the horizontal asymptote. There will only be one if there are any at all. Okay, so let's go ahead and get started on our first problem. So I'm going to follow my own advice here, and I'm going to factor this problem first. So when I factor this, my numerator stays the same for now. My denominator is 2x plus 5 times x minus 3. Even if this didn't cancel, this would be important to factor because it helps you find the vertical asymptotes. But when we did this, and we're canceling out the x minus 3, that is now kind of creating the very first thing that most people see, which is the hole, which is then, of course, actually in calculus called the removable discontinuity. Okay, so you have a removable discontinuity at 3 comma something. So then we want to figure out what that y value is that goes with the 3. To figure out that y value, so now I'm going to go ahead and type again. You substitute the x value, so in this case 3, into the simplified form of the function. So in our situation here, that simplified version is 1 over 2x plus 5. So I'm going to substitute 3 into that, and we're going to get 1 over 11 when you do that. So the whole will be at 3 comma 1 over 11. So that's the first thing I think most people notice. And then you're going to go and you have to find the rest of the stuff that's necessary to graph it, right? So now we're going to find, let's do the vertical asymptote next. So remember that vertical asymptotes occur when you set the factors in the denominator equal to 0. So in this particular situation, that is going to be 2x plus 5 is equal to 0. So that makes my vertical asymptote be negative 5 halves. Notice that I did that and wrote it as x equals and did not write just negative 5 halves, because that would just be a number, and we want to know specifically what we're talking about. So make sure that you write it as x equals negative 5 halves. The horizontal asymptote then is when you look at the simplified function. So simplified function, and use the end behavior rules on that. On this problem, my numerator is less than my denominator's power, which means that my end behavior it's approaching 0. So that creates my horizontal asymptote at y equals 0. So I'm going through this problem really slow because I know that these can be really confusing. So I'm going slow, and then the next one I'm going to go significantly faster through. Now we want to find any x-intercepts. Okay, you find x-intercepts by setting factors in the numerator equal to 0. On this problem, we don't have any factors in the numerator, so there are no x-intercepts. Now we want to find the y-intercept, if there is one. To find the y-intercept, you substitute 0 in for x in the simplified function. So in our problem, that is going to be, it was 1 over 2x plus 5. So I put 0 in for x. That gives me 1/5. So my y-intercept happens to be 0, 1/5. And it is a point, so write it as a point. Don't just write the number 1/5. Everything needs to be written in a way that makes sense mathematically. Okay, so a y-intercept is a point, so write it as a point. All right, whole bunch of information I now have to graph. So when I go to graph, I usually graph the vertical asymptote first. And then if there is a horizontal one, I graph the horizontal one. So that was 0. And then I graph the y-intercept and the whole next. So my y-intercept was 0, 1/5. So about here. And my whole is at 3, 1/11. So it's below, smaller than the 1/5. And then once I do this, I start testing values, but you want to remember limits and vertical asymptotes. So you always have to get closer to the vertical asymptote on either side of it. It's just a matter of which direction you're going. Are you going up like this, or are you going down like this? So up on the right side or down on the right side. So then you want to use a lot of the clues that come with the problem you're working with. This function that we're working with here already has 2 points that are above the x-axis. So since we already have 2 points that are above the x-axis, and notice that this one at 3 is lower than the one at 0, you can kind of deduce that the graph is going to go up like this. Also, any number that you put in the denominator, this would be like a number line test situation now, any number that you put in here that is bigger than -5/2, that's what that's supposed to be. I didn't label that very well. Any number that is bigger than -5/2, let's actually move the line over. Of course, it doesn't move all of it. It doesn't look like it's where it's supposed to be. Okay. So like -2, -1 makes positive values. So the whole graph has to stay positive. And since we have to get closer to the vertical asymptote, by definition, that vertical asymptote means you're going towards positive or negative infinity on either side. So since I have to get closer to it and the values are already in the positive regions up here, this is the only option. So now we have to decide what's happening over here. So this would be a good example of doing the number line method again. So let's say if that's -5/2, we could do -3, -4, negative whatever. You put a negative number to the left of -5/2 into this simplified function, you're going to get a negative number. The more negative the number is, so the farther to the left we go, the closer we're going to hug to the horizontal asymptote, because that's what we're being told is going to happen by the nature of it being a horizontal asymptote. And we have to get closer to the vertical asymptote. Since we already know the values are going to be negative, the only option is to go like this. Okay, that was all of the work for one problem. And I'm sure that you're a little confused because there's a lot that goes on in one problem. So we're going to continue. I'm going to do another one. And I'm going to do my best to continue to give you as much information that I can possibly think of as I'm doing the graphing. So here's the second one. And it's already factored for us, so that's pretty nice. So I'm just going to start listing out all of the information that we have. So let me get a different color here. Okay. So right away, I see that there is a vertical asymptote at x equals 5. And remember, that comes from the denominator being set equal to 0. So vertical asymptote at x equals 5. That square down there is doing something special, and I'll talk about that in a little bit. There is a horizontal asymptote at y equals 0 because the numerator's power is less than the denominator's power. There is an x-intercept at -4, 0, because when I set the numerator equal to 0, I get -4 for x. There is a y-intercept at 0, looks like that's going to turn out to be 4/25 because we put 0 in for x. There is no removable discontinuities because there's nothing that cancels in the numerator and in the denominator. I have 4 pieces of information. I do want to point out to you that when we say something has a horizontal asymptote, we are saying that the limit as x approaches infinity of our function, r of x, is equal to 0, our horizontal asymptote. And when we say something has a vertical asymptote, what we are saying is that the limit as x approaches 5, okay, so now we're saying, as x approaches 5 from the right or the left, it's either going to positive or negative infinity. So around 5, we're trying to figure out which direction we're going. And that square down there is going to help us figure that out. All right, here we go. Let me get the skinny line here. So 1, 2, 3, 4, 5, that's my vertical asymptote. 0 again is my horizontal asymptote. My x-intercept, 1, 2, 3, 4. Right now, if we were in class, what you would all be saying is, Mrs. Hasey, that's an asymptote. And you just put a point on the asymptote. And I'm going to tell you, surprise, that's okay. You can cross the horizontal asymptote. The horizontal asymptote is a guide, not a value that you can't have. It's just a guide to graphing, okay? It's something to tell you as you go to the left or go to the right, you're going to have approaching that value. A vertical is something you cannot have because you can't divide by 0, so that's why you can't cross the vertical ever. But this is the only place we're going to cross that horizontal asymptote. That's it. We just found it because it's the only x-intercept. All right, and then we've got 4/25. Yeah, I don't know. That's awfully hard to plot. We're just going to put it right there. Okay, so you've basically got 3 regions in this graph. You've got stuff to the left of the x-intercept, stuff between the x-intercept and the vertical asymptote, and stuff on the right side of the vertical asymptote. So 3 kind of regions that we're looking at. So we're basically going to test values in each of the regions. So let's test something over here, like anything that's bigger than 5. So like 6. Okay, so you're going to put 6 in for x into your rational function. When you put 6 in, all you care about is if it's positive or negative. So it's positive, okay? So that means in the region to the right of 5, you have to be approaching positive infinity on this side and then hug close to the horizontal asymptote as you go towards infinity. Now we're going to test in the region between -4 and this 5. We actually have already tested, so we already know. The y-intercept is a value we can use to test, but you could, if it makes you feel better, put any number you want between -4 and 5 in, and you are going to get a positive value. So +1, -1, it doesn't matter, you're still going to get positive values. So that means our function is going to approach positive infinity from the left side of that vertical asymptote as well. And then it's going to come down and touch or cross through the y-intercept. And now we have to figure out what's happening at that x-intercept. So now I need to plug a value in. We know this region's positive. I want to plug a value into the left of -4. So this is where it's going to change now. So -4, if I put something like -5, -6, -100, negative whatever, the numerator stays positive. Sorry, the denominator stays positive and the numerator goes negative. So that means we're crossing over the horizontal asymptote, but then staying and hugging close to that horizontal asymptote as we go off to the left. It's really hard to do with my stylus on my computer here, but it is creating this hugging close to the horizontal asymptote and not crossing again. So here's the thing. We could have actually determined pretty quickly what was happening around that vertical asymptote by looking at the fact that there was a power on that vertical asymptote that was even. So x minus 5 was squared, and since it was an even power, your function behaves in the same way on both sides. So my function went to positive infinity on both sides of that vertical asymptote. So I really only needed to try one side to get the graph correct, or to at least know what was happening around the vertical asymptote. All right, I've been doing this for a while and we've only done 2 problems. I'm going to find another one that I think will be beneficial for us to do next. I think we're going to skip this one on your paper for now and jump instead to this one. Okay, so this is number 4, I believe, on your handout if you printed it out. So first thing on this one, like we've been talking about, is factor first. So I'm going to factor the numerator, factor the denominator, see if anything cancels. If it doesn't cancel, it doesn't matter because we still need to have those vertical asymptotes and the x-intercepts. So this factors into 3x plus 1 times x minus 1. And then the denominator factors into x minus 2 times x plus 1. So this is creating 2 x-intercepts and 2 vertical asymptotes right away that we can see. So my vertical asymptotes are x equals 2 and x equals -1. And my x-intercepts are -1/3, 0, and 1, 0. Now I can go ahead and find my y-intercepts. Well, there's only one, right? So y-intercept of 0, comma. Okay, so I have been telling you to put it into the simplified part of the problem here, but I don't know if that's very helpful here. I think it might be easier to put 0 in for x over on the original function, because this is 0, you get -1. This is 0, you get -2. So you get that your y-intercept is a half. And then you need to figure out your horizontal asymptote. And that is going to come from looking at the highest powers in the numerator and the denominator. So the highest power in the numerator is squared, so is the denominator. So this creates a horizontal asymptote with leading coefficients of 3 over 1. So your horizontal asymptote is 3. Okay, so now here comes the last trick to the problem. I'm going to start graphing it, and then we're going to talk about something else that you need to think about as you continue to graph accurately. So I have +2 for a vertical, -1 for vertical. I have a horizontal at 3. I have x-intercepts at -1/3 and +1, and a y-intercept at 1/2. Okay, most people right away figure out that this region of the graph right here is going to make like a little parabolic shape, which I hope makes sense. Okay, you can't cross over this vertical asymptote, can't cross this vertical asymptote. Here's another little helpful hint. Okay, these powers, the powers on the x-intercepts that are in the numerator, those powers are odd. And when you have an odd power on a 0, okay, so on your x-intercept, so the factor in the numerator, this is going to be a cross-through point, just like you had before. And if it was an even, then it's a bounce point or touch point, whatever you were calling it. Okay, so both of these are odd powered, so that means these are cross-through points. So this graph has to cross over 1, has to touch the y, cross through the y-intercept, has to cross through at -1/3, and it has to get closer to these vertical asymptotes. Okay, so to come down this way and then to come down like this, it would then have to turn and cross again to come through this point. So it doesn't really make any sense. So the only real option that we have on this problem is to kind of make this shape be parabolic. So it comes up, crosses, touches, crosses, turns and backs down. Okay. All right, now the rest of it, we have to figure out what's happening on either other side. So remember how I told you in the last problem that if the power is even on the horizontal asymptote, then they go in the same direction. Well, if the power is odd on the horizontal asymptote, then the graph goes in opposite directions. Okay? So that means that I have to go up this way and I have to go up this way. The question is, do we cross the horizontal asymptote? And again, you're probably going, why would we ask that question? I don't know why. Because you're going, why? Why would we need to ask this? And I'm thinking, why wouldn't you ask this? Okay, so we need to figure out if we do. The way we figure out if we cross the horizontal asymptote, let me move this up a little bit, is we get a different color. We set the function equal to the horizontal asymptote and solve for x. If we get an answer, we cross it. If we get nothing, then we don't cross it. Seems easy enough, I hope. So I'm going to do that down here. So it was 3x squared minus x minus 2. Nope, I am wrong with that. I got my x and my y's in the wrong spot. Sorry. 3x squared minus 2x minus 1 over x squared minus x minus 2. My horizontal asymptote is 3. So we are trying to figure out if it crosses it, okay? And you do want to check this every single time because it's going to cross sometimes, as we saw in that last problem. Okay, so what I did is I just cross multiplied. Let's change the color. I said change the color. Okay, so I'm cross multiplying. And what you'll notice now is, well, the x squareds cancel. I'm going to, let's say I'll bring the 6 this way, I get 5, and I'm going to bring the 2x this way, and I get x. And so this is actually going to cross the horizontal asymptote at 5, whatever I get when I put 5 in for x. oh wait, what am I going to get when I put 5 in for x? You better get 3 because that's what we just said it was equal to, right? So if I were to put 5 in for x here, I'm literally saying when I solved for x, I got 5. I was solving it when it was equal to 3. So it better be the point 5, 3. Otherwise, we did something wrong. Okay. All right. So now I am going to scroll back up so I can finish graphing it. Okay. So 1, this was 2. 1, 2, 3, 4, 5. So 5, 3 is going to be a point on my graph. And then it's going to come down like this. And on the right side, it's going to hug. And on the left side, it's going to hug, but above. So it's not going to cross on the left. So it's not a perfect symmetrical graph or anything like that. I know these are hard. Okay, so we are going to be doing more in class. I'm going to stop here because I don't want to overwhelm you with too many practice problems on a long video. So we're going to stop with 3 of them, and then we will be going over bunches more in class, okay? Make sure that you have written down any questions you might have.